Hey everyone, welcome back. So we're going to continue on our study of integration techniques. One thing you might have noticed in the past, one thing that makes integrals difficult is square roots, right? Square roots just, they can screw things up. There's no nice formulas for them. So what we're going to do today is we're going to talk about a technique, and it's called trigonometric substitution, that allows us to deal. Let me get that written. So trig substitution is a technique that allows us to deal with square roots that show up in integrands. So I'm going to make a little table here, and we're going to need this table. So this table, it's going to have three columns. So the first column labeled expression, the second one substitution, and the third column will be identity. Okay, so what we have on the left-hand side, the first of our expressions, a squared minus x squared. Now, if your integrand involves an expression of this form, some constant squared minus the variable x squared, then we're going to make a certain substitution. X equals a times, and that's an a there, a times sine theta. And then we're going to make use of a trig identity that will allow us to get rid of the square root. And the trig identity is the standard one, cosine squared theta plus sine squared theta equals 1. Right? So this idea behind trig substitution, we'll see how this goes, but the idea is to take advantage of certain trig identities that will allow us to deal with the square root. So here's the first form. The second expression, something in the form square root of a squared plus x squared. In that case, we make the substitution x equals a tangent theta, right? And then we'll take care, or we'll make use of the identity 1 plus tangent squared theta equals secant squared theta. And then the last of the expressions that trig substitution is designed to help with is square root of x squared minus a squared. In that case, we'll make the substitution x equals a secant theta. And we'll take advantage of the trig identity, same one as above, 1 plus tangent squared theta equals secant squared theta. Okay, so trig substitution is designed to help us deal with integrals that involve integrands that have one of these three forms right here. Now, throughout all of this, let me see how I'm going to say this. So we assume that x is such that that what? Or yeah, let's say x is chosen such that x is chosen whatever trig function we're working with. So trig, I'll just say trig theta greater than or equal to 0. So because we're going to be taking square roots of squares, and we want to make sure that we get the positive output when we do that. So this is just sort of a technical assumption that we'll assume throughout. Okay, so let's just jump in and start doing examples and see how trig substitution works in action here. So first example, let's do square root of 4 minus x squared divided by x squared dx, right? So this one right here is tailor-made to do trig substitution to, and notice it falls into this category right here. Whoops, I just stepped out of the shot. Falls into this category of the square root of a squared minus x squared. So what we're going to do, in this case, a is equal to 2 because I've got a 4 right here. So our substitution is going to be x equals 2 sine theta. We need to compute dx, so dx is equal to 2 cosine theta d theta. And now I'm going to go back and substitute. So let's see what we have. So this will be integral. Under the square root, we're going to have a 4 minus 4 sine squared theta. In the denominator, we will have a 4 sine squared theta. And then remember, dx has to be replaced with 2 cosine theta d theta. That's important when you're doing trig substitution. Make sure that not only everywhere you see an x, you replace it with the appropriate trig format. You also need to replace the dx with the appropriate part. Okay, so now let's see what we got. Notice right here we've got 4 minus 4 sine squared theta. And I'm kind of running out of room here. I'll write it up here. So what we have, 4 times 1 minus sine squared theta if I factor the 4 out. And then this piece right here, according to this identity, if you solve, that's equal to cosine squared. So this is equal to a 4 cosine squared theta. Which means then that right here I can replace what we see under the square root with a 4 cosine squared theta. Everything else I'll leave the same, so I've got a 4 sine squared theta and then a 2 cosine theta d theta. Okay, so this is good. Now I can take the square root of that perfect square. So that's the point. Trig substitution is designed to get a perfect square under the square root, and then we can get rid of the square root and finish off the integral. So let's keep going now. Things are going to start falling apart. So this then becomes 2 cosine theta over 4 sine squared theta times 2 cosine theta d theta, which we can then write as, well, okay, let me just write it like this. So I've got a 4 in the numerator, 4 in the denominator. That's going to cancel. And so what we'll have is cosine squared theta over sine squared theta d theta, which you can write as cotangent squared if you like. There's a couple of different ways to go about this now. What I'm going to do is just use one of my trig identities. I know that cosine squared is the same as 1 minus sine squared theta. And then I have a sine squared theta here. And then if we keep going, this will give me a cosecant squared theta minus 1 d theta. So here's the point. When we do this trig substitution business, what it's going to do is it's going to give us an integrand that is a mixture of trig functions. And that's why we did the previous section, right? We learned how to integrate products of trig functions precisely so that we could do trig substitution and actually compute these integrals. Okay, so this is going to give us then a negative cotangent theta minus theta plus c. Now we're not done, but the whole point was once we got to the final step here, we had an easy integral to compute. Now, my answer at this point involves the variable theta, but the original integral involved the variable x, so we need to get back there. And here's the next step. So let me write down my substitution again, right here. X equals 2 sine theta was my substitution. And so I can rewrite this as a sine theta equals x over 2. And now what I'm going to do is draw a triangle, and I'm going to label it according to this equation right here. Let's see, sine theta, that's opposite over hypotenuse, and so I'm going to have an x and a 2 right there. And then using Pythagorean theorem, I can label this lower one as a 4 minus x squared. Now, why am I doing this? I need to figure out what cotangent of theta is, based on this substitution right here, that sine theta equals x over 2. Let's see now, cotangent, that's adjacent over opposite. Adjacent over opposite. So reading off from this triangle, what we get is cotangent theta equals adjacent over opposite. And so now I can come back in and fill in the blanks. This will be a negative square root 4 minus x squared over x minus theta. Now what's theta? Well, I can solve right here. Theta is arc sine of x over 2, or inverse sine of x over 2, and then we have a plus c. So this is the way these problems are all going to go. We do a substitution, trig substitution. Once we simplify things, what we'll have is a product of trig functions, which we have techniques for integrating. Once we've integrated, we're going to get an answer that involves the variable theta. We need to convert back to the variable x, and creating the appropriate right triangle is going to allow us to do that. Okay, so let's try another example. Okay, so next example is going to be integral x cubed over square root of x squared plus 9. So if you take a look at the table, this tells us that we're going to do a tangent substitution. So I'm going to let x equal 3 tangent theta, in which case dx equals 3 secant squared theta d theta. And now let's substitute. Everywhere I see an x, I'm going to replace that with a 3 tangent theta. I'll also replace my dx. So this will be a 27 tangent cubed theta. The denominator, we're going to have so this will be a 9 tangent squared theta plus 9. And then the dx is a 3 secant squared theta d theta. All right, so remember, trig substitution is designed to deal with these square roots right here. So if we look at this piece right here and look at the substitution, or the identity portion, what we know is that 1 plus tangent squared theta is equal to secant squared theta. Now, if I multiply through this equation by a 9, what we get is a 9 plus 9 tangent squared theta equals 9 secant squared theta. And so under the square root, I can rewrite as 9 secant squared theta. So we get a 27 tangent cubed theta. Under the square root, we have a 9 secant squared theta. And then we get a 3 secant squared theta d theta. Let's get rid of the square root now. So this is a 27 tangent cubed theta times 3 secant squared theta. And then this will become a 3 secant theta like that. And now let's cancel some stuff and clean some things up. This will become, so notice the 3's cancel and one factor of secant cancels. So what we'll have, I'm going to put the 27 out in front. So it'll be 27 tangent cubed theta times secant theta d theta. So what do we have here? A product of trig functions. I've got an odd power of tangent, right? With a mixture of tangents and secants, we've got an odd power. And we know in that case then, what do? Peel off a factor of tangent and secant. So we'll have a tangent squared, and then we'll have a tangent theta, secant theta, d theta. Next step, apply trig identity right here. We know that tangent squared theta is equal to a secant squared theta minus 1. Like that. And now we're set up to do substitution, u substitution. Here I'm going to let u equal secant theta, du equals secant theta, tangent theta, d theta, and now we're going to convert this into the integral of a polynomial. So what do we have? 27 integral, and then this will be a u squared minus 1 du. Now we've got an easy integral. This becomes 27 integral, 27 times u cubed over 3 minus u plus c. Okay, so there's an answer, but that's not the final answer, right? Our answer at this point involves the variable u. We started off with the variable x, and we did two substitutions, right? We first converted, we went from x to theta and then theta to u. So we're going to have to do two backward substitutions now. First, we know that u is equal to secant theta. So this becomes 27 times secant cubed theta over 3 minus secant theta plus c. So now we have an answer that involves the variable theta. This is the time to draw the triangle. All right? Every time when you get to this step right here, you draw a triangle to find out what the various trig functions are in terms of the variable x. So I draw my right triangle, and I label it according to our substitution. And our substitution this time, it was x equals 3 tangent theta. And so that means that tangent theta equals x over 3. Label the triangle according to our substitution equation, which means, remember, tangent is opposite over adjacent. And then Pythagorean theorem allows us to find the other leg. This will be a 9 plus x squared. Okay, now in our equation over here, or our answer over here, we need to figure out what secant is. Let's see, secant is hypotenuse over adjacent. Right, so reading off from this triangle, what we get is secant theta is equal to hypotenuse over adjacent, like that. And so now we go back to our answer, 27 times, let's see, secant cubed. So I'm going to cube this piece right here. That's going to give me 9 plus x squared to the 3 halves divided by, well, it's going to be a 27, and then there's another factor of 3, so it's actually 81 right there. And then we'll say minus square root 9 plus x squared over 3 plus c. If you want, you can clean this up a little bit more by multiplying that 27 through, but that's really not necessary. Here's the answer. All right. One thing to notice here, these problems are a little bit involved, right? I mean, so far we've done 2 problems, and let me see how long I've been going. I've been going 19 minutes. So these problems take a bit of work to get through. And so let's do some more examples just to see what kind of other situations may arise. So let's see, next example. Let's do integral dx over square root x squared minus 6x plus 13. This doesn't, at first glance, does not fit any one of the 3 forms. But it is a quadratic polynomial under a square root, right? And that, at least gives us a hint that maybe trig substitution will still work. The idea is, before I can go any further, I need to complete the square. So let's write this out. X squared minus 6x plus 13. Let's see, how do you complete the square? You take the middle term, cut it in half, and square it. So we'll have an x squared minus 6x, cut it in half, and square it. So that will be a minus 3 squared, gives me a 9. And then I'm going to add and subtract 9. And so we get x squared minus 6x plus 9 plus 4, which is equal to now x minus 3 quantity squared plus 4. So I can write under the square root this quadratic polynomial re-expressed like this. So it'll be square root of x minus 3 quantity squared plus 4. And so now this suggests that we're going to actually do a tangent substitution. Let's do a u substitution first, just to get it into place. So I let u equal x minus 3 du equals dx. And now we have, let's see, dx is du, so du over square root of u squared plus 4. Now it's clear that this is going to be a tangent substitution. So remember this, if you see a quadratic polynomial under the square root, and it's not exactly matching the standard forms, meaning that it's got a degree 1 term in the quadratic polynomial, then completing the square is the way to go. All right, now we're set up to do a substitution where I let u equal 2 tangent theta, du equals 2 secant squared theta d theta. And now when we substitute, what we'll get is, let's see, so du is a 2 secant squared theta d theta, and under the square root, we've got a 4 tangent squared theta plus 4. So let's see if we can get a little bit quicker now. That right there can be replaced with a 4 secant squared theta. Because it's under the square root, we can kill that off. And so what we'll have is a integral 2 secant squared theta d theta on the top. And then the denominator can be rewritten as 2 secant theta. All right, so I applied the identity. I skipped some steps here. Hopefully you can keep track of these. So rewrite this. This becomes a 4 secant squared, the 4 tangent squared theta plus 4 becomes a 4 secant squared theta under the square root. When you take the square root, here's what you're left with. Cancel out the 2's and 1 factor of secant, and what we have is integral secant theta d theta. And we learned a formula for the integral of secant theta last time. That's equal to natural log absolute value secant theta plus tangent theta plus c. Okay, now it's time to draw the triangle, labeled according to our substitution equation, which is right here. So if I take that equation and rewrite it, what we have is tangent theta equals u over 2. So I'm going to label opposite over adjacent, and then this becomes a square root of 4 plus u squared. All right, so what are we looking for? I need to know what secant theta is. Secant theta from this triangle. So secant is a hypotenuse over adjacent. Okay, so now we can come back over here and substitute. This becomes natural log absolute value. Secant theta is square root 4 plus u squared over 2. And then tangent theta, well, tangent theta is u over 2. We're almost done. But remember, the original problem asked or was asked in terms of the variable x. And so now everywhere I see a u, I need to replace with what u was. And let me think, u was equal to x minus 3. That was our substitution. So final answer, this is equal to natural log, absolute value, square root of 4 plus x minus 3 squared, all over 2, plus x minus 3 over 2 plus c. Okay, I want to do a few more examples still. These problems can be given to us with various wrinkles in them, you could say. So the next example, so this will be integral dx over x squared times square root 16x squared minus 9. Okay, so what's different about this one versus the previous ones? Now we have a 16 as the coefficient on the x squared, right? In all the other previous examples, we just had a 1. So we need to handle that, and there's a couple different ways to handle it. One way to handle it is just to factor the 16 out. And so that would go like this, dx x squared square root 16 times x squared minus 9/16. And then we can pull the 16 out of the square root, which becomes a 4, and then all the way out of the integral. So this would become a 1/4 integral dx over x squared square root x squared minus 9/16. Now it's set up to do substitution. In this case, it's a secant substitution, where, let's see now, how's this going to go? X is equal to 3/4 secant theta, right? In this case, we have an x squared minus a squared, where a is 3/4. Okay, then we compute dx. We get 3/4 secant theta tangent theta d theta. And then when we substitute back, what we'll have is a 1/4 integral. It'll look a little bit messy for a minute. 3/4 secant theta tangent theta d theta. Denominator is 9/16 secant squared theta. And then under the square root, we'll have a 9/16 secant squared theta minus 9/16. So it looks a little bit messy, but it should fall apart nicely in a second. Let's see. We need to handle this square root right here. And what do we know? We know that secant squared theta minus 1 is equal to tangent squared theta. So right here under the square root, I'll do this in steps here. So this is a 1/4, 3/4 secant theta tangent theta d theta. 9/16 secant squared theta. And then right here, this is going to be a 9/16 tangent squared theta. All right, so now let's take the square root. This will be a 1/4 integral. 3/4 secant theta tangent theta d theta. Denominator becomes a 9/16 secant squared theta. And then we'll have times a 3/4 tangent theta when you take the square root. Okay, so now let's start canceling stuff. The 3/4 cancel. The tangents cancel. One factor of secant cancels. And so when you simplify and do all the arithmetic, so let's see, I need to flip that and multiply, so that's going to give me a 4/9. And I'll put that outside of the integral. So this is just, if you multiply 16/9 times 1/4, you get 4/9. And then I have secant theta in the top, secant squared theta in the denominator, which leaves us with a secant theta in the denominator, which becomes cosine theta d theta. So that's the easy integral. Now we get a 4/9 sine theta plus c. So everything looked like a mess, but in the end it fell apart and gave us a very easy integral to compute. All right, now it's time to draw the triangle. And oh shoot, I wish I would have erased that. My substitution was what? X equals 3/4 secant theta. That's what it was. Which means, let's write it, so let's solve now. Secant theta is equal to 4x over 3. Secant is hypotenuse over adjacent, so I get a 4x here, a 3 here, which means that I get a 16x squared minus 9 over here. And so from this triangle we can read off what sine theta is. Sine theta equals opposite over hypotenuse. So in the end what we get is a 4/9 times this stuff, so the 4's cancel. Let's see if I can write this nicely as a square root 16x squared minus 9 divided by, let's see, the 4's canceled, so I'm just left with a 9x plus c. Okay, so far we've done trig substitution for antiderivatives. We haven't seen it at work on a definite integral, so let's try that now. So let's look at this one. Integral 0 to 1, the square root of x squared plus 1 dx. This, it should be clear, is a tangent substitution where we let x equal tangent theta, in which case dx equals secant squared theta d theta. And so now, remember, when you do a substitution, you have to change the limits. And now notice, these are x limits. When x equals 0, we have tangent theta equals 0, which means that theta equals 0. When x equals 1, put the 1 in place of x, we have tangent theta equals 1. That means that theta equals pi over 4. And then under the square root, we'll have a tangent squared theta plus 1. We'll have here secant squared theta d theta in place of the dx. Under the square root, that's a secant squared. When you take the square root, this right here becomes a secant theta, and so what we have is integral from 0 to pi over 4 secant cubed theta d theta. Now, this is not one that we've studied when we were studying products of trig functions. This one's kind of a pain. You have to do integration by parts, and I think this will actually be on your quiz. On your next quiz, you'll have one that involves going through the integration by parts to find the integral. What I'm going to do is just write down the formula for the antiderivative of secant cubed. So it's going to be 1/2, let me make sure I get this right, 1/2 times secant x tangent x plus natural log, let's make sure I got this, is it plus? Yeah, plus natural log of secant x plus tangent x plus c. I definitely do not expect you to memorize this formula or even really know how to do it. You'll see how to do it on the quiz. Oh, sorry, we're doing a definite integral, so it's not plus c. It's 0 to pi over 4. So, oh, sorry, and I put x's here. These should be thetas. Sorry, that's a theta there. Theta. Everywhere I wrote x, please replace that with a theta. Okay. And now we can plug in the limits of integration. So this will be a 1/2. Secant of pi over 4 is a root 2. And tangent of pi over 4 is 1. And then we'll have plus natural log. So let's see, pi over 4 gives me a root 2. And tangent is a 1. When I plug in 0, I'm going to get, well, I'll get 0 here. I'll get natural log of 1 plus 0. So that's 0 all the way through, right? Because natural log of 1 is 0. So there's the answer. Now, one thing to be aware of, when you do trig substitution with a definite integral, you change the limits as you go. And notice I didn't have to draw a triangle. I just plug in the limits of integration. So it's definitely in your best interest. I think I said this right when we were first learning or reviewing U substitution. Learn to change the limits. Here is one important reason. Otherwise, you'd have to do back substitutions with a triangle and then plug in the original limits. Right? I want to do. Well, I don't want to complete this example, but I want you to be aware. Trig substitution is designed to handle square roots. But just because you see a square root doesn't mean you absolutely have to use trig substitution. So, and you'll have a couple of homework problems like this that are not trig problems, but it's designed to make you recognize, oh yes, you could do tangent substitution, go through the trig substitution process, but it's much quicker in this case to do U substitution. Okay? So, just because it has a square root does not mean that you absolutely have to do trig substitution. There's sometimes more than one way to do it. Here's an example. All right, do U substitution. It's much quicker, much more efficient if you can do U substitution rather than trig substitution. Now, one last thing. We've been talking and doing examples of situations where we do trig substitution. Trig substitution is designed to help you deal with square roots, but that's not the only situation. So, trig substitution can also be used for other powers. Meaning, right, so what we've done so far, we've looked at things like this, a squared plus or minus x squared, and so on. With a square root, well, remember a square root is a 1/2. So when I say other powers, what I mean is powers other than a 1/2. Right? So when you see quadratic polynomials raised to various powers, not necessarily 1/2, trig substitution is often the way to go. So let's look at this example here. Let's do integral dx over 9x squared plus 1 raised to the second power. So instead of a 1/2 and a square root, what we have is we have it raised to the second power. Now, the first thing I'm going to do is I'm going to let u equal 3x. Right? This should make you think of tangent substitution, but I've got a 9 here, and so the way to handle that, or one way to handle that, is to let u equal 3x, then du equals 3 dx. And what we get is, so let's see, this will be a, let's see, dx, if I solve, is a du over 3. So this is going to be a 1/3 integral du over u squared plus 1 quantity squared. Now it should be clear that we can do a tangent substitution where we let u equal tangent theta, in which case du equals secant squared theta d theta. And now, let's put it down here, this becomes a 1/3 integral secant squared theta d theta divided by, let's see, this is a tangent squared theta plus 1, all that squared. If we were doing square root stuff, we'd apply an identity right here, and then the square root would kill off the squared. In this case, though, it's raised to the second power. I'm still going to apply the identity. So this is a 1/3 integral secant squared theta. Right here inside, that's a secant squared theta. It's being squared, so I get a secant to the 4th theta d theta. Now things are going to cancel nicely. This becomes a 1/3 integral. So let's see, this will be a 1/secant squared theta, which is the same as cosine squared theta d theta. Now remember how to integrate a cosine squared. We've got an identity that allows us to deal with that one. So we'll have 1/3, and then we get a 1/2 times 1 plus cosine 2 theta d theta. Okay, I got to remember which substitutions I did. U equals 3x and then u equals tangent theta. So this becomes a 1/6 integral 1 plus cosine 2 theta d theta. Now we've got an easy integral. This is a 1/6 times theta plus 1/2 sine 2 theta plus c. Now we've got an answer, and I just need to remind myself, okay, so that was u equals tangent theta was the substitution. So now it's time to draw the triangle. Labeled according to, so we had u equals tangent theta. You can think of that as a u over 1, right? So tangent theta, that's opposite over adjacent. So I get a u here, a 1 here, and then that will be a square root of 1 plus u squared. Okay, so this triangle now, I could read off any trig value. Tangent theta, sine theta, cosine theta, whatever, secant theta. The problem is we've got a sine 2 theta right here. So I need to apply an identity right now. Sine 2 theta, right, so sine 2 theta equals 2 sine theta cosine theta. I need to get everything in terms of having arguments not multiplied by 2, so just plain old theta rather than 2 thetas. So this becomes a 1/6 theta plus, when I substitute here, we'll get a sine theta times cosine theta plus c. So from this triangle then, sine theta equals, so sine theta is opposite over hypotenuse, so that will be a u over square root of 1 plus u squared. Cosine theta is an adjacent over hypotenuse. So when we finish this off, what we have is a 1/6. Theta is arctangent of u. So we get arctan u plus, now it's sine theta times cosine theta, so that's the product of these two right here. So that will be a u over 1 plus u squared plus c. Now, I'm almost done. We've got the answer in terms of u. We need it to be in terms of x. And we had u equals 3x. So everywhere I see a u, I'm going to replace it with 3x, and then we'll be done. So this is a 1/6 times arctan of 3x plus 3x over 1 plus 9x squared plus c. Okay, so trig substitution, the problems can get a little bit involved. So if you notice on the homework, I think I gave you about 7 or 8 problems like that. You want to work through each of the various types, right? They show up in various ways, and this is an important technique to know. Okay, so we will see you next time.